We are going to cover two quick units that I missed out on in part 3. So this will go quick. Charge sharing. So these questions come up on the regions every once in a while, and they involve the law of conservation of charge. The law of conservation of charge is like any conservation law, which states that whatever we start with is whatever we finish with in a closed system. So what's the definition? The total or net charge of a system must remain constant. We could also write that with sigma, which means summation. The sum of all the charge that we start with has to equal the sum of all the charge that we finish with. So let's take two metal spheres, and let's say the first one is charged up with -6 coulombs, and the second charge is charged up with +2 coulombs. Well, what's our net charge of the system? -6 plus 2, the total is going to be -4. That's our net, that's our total charge. Well, what happens if we take these two and we touch them together and then separate them? Remember that everything in charge wants to go to the lowest state possible. It wants to even out. So what's the evening out? Well, there's a formula for this, and it's not on the reference table. I write it this way. Q share, the sharing of the charge, is equal to charge 1 plus charge 2 divided by 2. In other words, it's an average of the two. If they did this with 3 spheres, it would be Q1 plus Q2 plus Q3 divided by 3. So these come together and touch. Then they separate. And we have 2 spheres. That one's not supposed to be small, but whatever. So Q share, let's go ahead and put our numbers in. So we have -6 coulombs plus 2 coulombs divided by 2. So what's Q share? Q share is going to be -4 divided by 2, so that's -2. So this sphere will have -2, this sphere will have -2 after the touching and the separation. Well, what's our net charge? -2 minus 2, that is -4, so the total has not changed. Now, they might try to make this a little more trickier, for example, by using numbers with exponents. So let's say they say that sphere 1 has 3.8 times 10 to the -15th coulombs, and sphere 2 has a charge of -2.1 times 10 to the -15th. The rule is exactly the same. There's no difference here. It's going to be Q share equals Q1 plus Q2 over 2. In other words, 3.8 times 10 to the -15th coulombs minus, because we're subtracting, it's adding a negative, so that's 2.1 times 10 to the -15th coulombs, all divided by 2, and that gives us a Q share of 8.5 times 10 to the -16th. That came out positive, so it's a positive charge, and that's the charge on each sphere. All right, this is the Millikan Oil Drop experiment, and most likely if you're asked questions about this on the Regents exam, they're only going to ask you questions about part of this experiment. But let me explain how it works. Essentially, what Millikan did was he took 2 metal plates and he used a voltage power supply. Now, we haven't learned about this yet, but the long side is positive and the short side is negative. So that's going to build up a charge on this plate of positive because it's removing electrons, and this plate is going to have electrons added to it, so it's negative. This is not an electron. This is an oil droplet that has built up some charge. So what he did was he took a little bottle that produced mist. Now, what mist is little tiny spherical droplets of whatever it happens to be. In this case, he used oil. And he ionized the oil droplets so that the oil droplets gained electrons. And those extra electrons on there gave it a negative charge. Well, what's going to happen? Well, this is going to repel and this is going to attract. So we're going to get an upward force of F E. But what he was able to do was to adjust the strength of the electric field so that he could get the negatively charged oil droplet to levitate. Now, if it's levitating, that means it's not moving, so its net force is 0. So Fg is going to equal Fe. Now, there's another piece of this, which is a formula that used to be on the old reference table. It's not anymore, which is that the strength of the electric field is equal to the voltage over here divided by the distance between the plates, d. So what Millikan was able to do was to determine the charge of one electron. He's the one who figured out that Q is 1.6 times 10 to the minus 19th coulombs. And the way that he did that was he started out with this formula E equals V over D, and then he applied E equals F over Q and set those equal to each other so that he got F over Q is equal to V over D. Now we know that force is Fe and that Fe is equal to Fg. So we can replace that with an Fg, and we can also say that that's Mg. So if we cross multiply, we take Mg times D and V times Q, and then divide that V or leave it there, we can end up with a new formula which is Q equals Mgd over V. So he knew V, he was able to figure out M somehow. I don't know how he did that. We know what G is, and he could measure the distance between the plates. The problem is that this Q was not the charge of one electron, this was the charge of the number of excess electrons. So what he did was he got numbers for lots of different oil droplets, and he found that the one number that evenly divided into all of the charges was 1.6 times 10 to the minus 19th. That's getting into some more depth that you don't really need to know about, but maybe if you're taking physics, your physics teacher will go into more detail on that.
Millikan's oil drop experiment. The famous method that he devised between 1906 and 1914 to measure the charge E of an electron is known as the Millikan's oil drop experiment. Using this method, he calculated that the charge on an electron was about 1.6 times 10 power negative 19 coulombs. In the Millikan's oil drop method, an atomizer produces oil droplets in the form of mist, which are sent through a plate of electrical condenser. There are different forces which act on the oil drop, including gravitational, electrostatic force due to electric field, and viscous drag force. The rate at which these drops fall were measured by observing them through a micrometer eyepiece of a telescope. X-rays were passed through the chamber to ionize the air inside. On colliding with gaseous ions, these oil droplets acquire charge. The rate at which these droplets fall can be controlled by changing the strength of applied voltage to the plate. With this experiment, he observed that the magnitude of electrical charge Q on the droplets is always a multiple of electrical charge E. That is, Q is equal to NE, where N is equal to 1, 2, 3, and so on. Using the value of charge of the electron, the mass of the electron, ME, was then determined by combining Thomson's value of E by ME ratio. The value shown is the value of the mass of an electron.
So again, the important idea here is that the oil droplet force, Fe, is equal to Fg. So let's say we have an oil droplet, and the oil droplet has a charge of 8 times 10 to the minus 19th coulombs. And therefore, it's going to have a force due to the Coulomb force, the electrostatic force up, and an equal force of gravity down. And let's say that we figured out that the mass of the droplet was 1 times 10 to the minus 4th grams. We have to convert that to kilograms, so that's moving the decimal 3 more places. So that's going to be to the minus 7th kilograms. And now, let's see if we can figure out E, and let's see if we can figure out the number of excess electrons. So to do that, To find Fg, we're going to have to find that Fg first. All we have to do is fugga mugga, Fg equals mg. So we have m, which is 1 times 10 to the minus 7th kilograms, times 9.8, and we multiply those two, and Fg is equal to 9.8 times 10 to the minus 7th newtons. So taking that in combination with E equals F over Q allows us to figure out the strength of the electric field. Remember that this F is Fe, but that in this case Fe is equal to Fg, so we can just sub that in. So what's Fg? That's 9.8 times 10 to the negative 7th newtons divided by 8, the charge, the excess charge, to the minus 19th coulombs. And if you do the math on that, you get 1.2 times 10 to the 12th newtons per coulomb. So let's figure out how many excess electrons there are. Well, we know that the charge is 8 times 10 to the minus 19th coulombs. Multiplying that by 1 electron per 1.6 times 10 to the minus 19th coulombs. Coulombs will cancel, and we're basically multiplying, but this is on the bottom, so we divide. And when we do that, we end up with 5 excess electrons.